guys go remote?
I don't know. I'm just like, I much prefer in person. And given that there's so many other people aren't staying in person, I feel like just me going online, I don't have to.
Because most of the soccer team is here.
Yes.
In person.
Yes. And the only class that I'm within 6 feet of people, the people are soccer people. So I feel like if they get COVID, soccer will already.
It'll mess the whole team
it'll
up anyway.
Really mess it up. Because I'm the only person in my gov class.
Okay, I remember telling you that I always get like one wrong. That's on the
This is
SAT.
funny.
It's so easy. One of the questions was
math is so hard.
one of the questions was 2x minus 3 equals 0. You did this all right.
One of the questions was
2 over 3.
slope of that line.
It's 2 over 3.
And then it graphs the line for you.
Well, like the thing is it starts off super easy,
I spent 1
and then
minute
it progressively gets harder.
4 times 200.
So the ones in the middle are the ones you're supposed to miss, where you think it's supposed to be easy.
What are you talking about?
Not really.
SAT, I don't know.
Oh.
I think that's what it's
Oh.
supposed to be.
Still easy.
I was like, what?
And then
No, it's
Classes
a linear
are-
test. It's a linear test.
Was I the only one who on the question where it asked how much of the vertex was the parabola, like the derivative of the parabola and set it equal to 0?
I didn't
I don't know if that was like,
I just grabbed it.
The derivative of the parabola.
look, like, they wanted us to like turn it into vertex form, and I completely forgot that vertex form
That's
existed, so I took its
opposite
derivative.
of
Joey-
video.
Joey would
I
know
just
it.
started. No, I just started.
They don't ask for derivatives on the SAT.
Joey-
No, they were asking for the vertex, so they wanted
Yeah, I
to
should
the
know.
vertex form.
Yeah.
I
started-
started-
No, vertex form is just like it's
Negative
just like
b over
it's
2a.
point- No, the vertex form is you have it like in the quadratic.
I got the right
The
answer.
vertex is a point.
You should you translate it into Spanish and then say, oh.
Is MATLAB allowed?
Bro, I can't count.
They should have those questions where it's like 16 dots and it's like, how many dots are there? That actually like probably trips people up.
Oh, dude, they had one about the median, and I like kind of forgot what the median was.
It was like the population of like
But it's like the cross
It was El Salvador.
Yeah.
it was like the third one down.
What math does the SAT go through? Like algebra 2?
Free algebra, I think. There
No,
wasn't like.
it's
Yeah,
algebra,
I remember
algebra
looking
2.
at
Tiny
stuff.
sprinkle of pre-calc on there?
Do what?
Isn't there like a tiny sprinkle of pre-calc on there?
Maybe on the essay.
Like what? Is there?
No, because you're supposed to take it as a junior. And you're not supposed to take pre-con till your senior year, right?
Yeah, I mean, a normal pace would be that you weren't in pre-cal till senior year.
Joey and Jesse are like, what? And Albert?
Bro, I can't count. That'd be hard.
Okay, Joey, you
Well-
took the derivative of the line. I just took the slope and saw what it had and then added.
I could see how.
Bro, you can just graph it.
I could see if you were like really far ahead, how it'd be like, oh, I don't remember doing that. That was a long time ago.
I only have 10 fingers. I can't count
Wait.
past that.
A chair has 4 legs. How many legs are in 200 chairs?
I was literally the first question.
Is that actually?
Yes. It was like,
So
my
it's-
chair has 4 legs and 1 seat. If a company wants to build 800 chairs, how many legs do they have?
All right, I guess we'll start.
200 chairs, and they need 800 legs.
They need
Just
a-
hoping the last people would show up.
Counts their chairs by the legs.
Who makes
I have 800
You don't do that?
legs worth of chairs. That's
Oh, of
all.
course.
Like, all right, we need one tri-stool, you know. Okay.
All right, guys, we are going to do lesson 10.
Still bad.
All right, today we'll do a lesson. Tomorrow is going to be just a work day. You guys have a problem set 3 due tomorrow. You have problem set 4 due Monday. You have a test on Tuesday. So I'm going to give you guys tomorrow to work on what you need to work on to knock some of that stuff out. Friday will be a MATLAB that won't be due for a week. So that's another day where if you were more concerned with problem set 4 or the test, you can use Friday as well to work on stuff for problem set 4 or the test, knowing that you're then deferring MATLAB to be due sometime a week later. Test, but you won't have a problem set due that next week because we'll have a test and we won't have had enough lessons to have a problem set. So if you defer the MATLAB, you won't have other things you need to work on for this class once the test is over. Monday, we'll do another group bonus thing. and then Tuesday will be your test. So that's basically what we have coming up left here. So today we're going to finish what's on their first test, which is going to be called the complete solution. It puts together a lot of what we've already done into kind of like, okay, what is my full solution to AX equals B look like? Meaning, what are all the intersections? Does it intersect in one place? Does it intersect in a line, in a point, in a plane, whatever? Okay, so that's kind of what we're looking at today, complete solution. So you want to make as many connections to the past lessons as possible, although this does just have a process that we're going to go through that you kind of could use. Let me do this thing. All right, so it is going to heavily use what we did in lesson 8. When we solved for AX equals 0, we found the solutions in the null space. Elimination converted this problem to UX equals 0. I showed you could go even further to R, reduced echelon form. We didn't really do that very much. I'm not going to require you guys to do that. R is just reducing it even further. You could solve that one. You could solve UX equals 0. You'll get the same thing. When we were doing that, we ignored the right side of the equation because we had zeros. And so if you add rows with a 0 to rows with another 0, you'll just get more zeros. So we weren't really concerned with what was happening to the right-hand side of our equations when we started messing with the left side of the equations. Our solution was the null space, basically. Okay, vectors in the null space. And what we actually got was linear combinations. Okay, of vectors. If we got any vector that was non-zero, we actually got infinitely many. Okay, we got every multiple plus any linear combination with other non-zero vectors would give me more vectors that made it true. So when we found that, we actually found like entire lines filled with them, or entire planes filled with them, or entire whatever, three-dimensional spaces filled with them. We didn't just get one, we actually got infinitely many because this is a space. Okay, so I can take linear combinations and still have more vectors in that same space. Today we're looking at what happens when B is not 0. So one thing that's going to change is what I do to the left side. I need to keep track of how that's affecting the right side as well. So we'll use an augmented matrix instead of just matrix A. So I'll put A and B next to each other. Oh my gosh, so slow.
Is it always?
Schultz just popped.
It like comes and goes. 8th period is usually the worst. I don't know why 8th period is like really slow internet or something.
Oh my God.
Wow. Okay, that's an A. There we go. All right. So we'll put them next to each other so that when I start messing with rows of A, it will do the same thing to the other side of the equation, because now the other side's not 0. We need to pay attention to what we're doing. Otherwise, we'll do the same thing we did before. We'll take A and reduce it to U. You could reduce it all the way to R if you wanted to, but we'll reduce it to U. B will change. C here, AX equals B going to UX equals C. C is just what happens to B when you do elimination to A. Okay, so B will also change. So that's what C is. It's just whatever constants remain after doing the elimination that you did. We'll find what we call a particular solution. Okay, this means we're going to set, well, you could set the free variables equal to whatever you want, but I would set them all equal to 0. It's the easiest thing to choose, and just solve for the pivot variables. When we did the null space, we did not want to plug in all zeros because all that would give us is the 0 vector, right? With the null space, we had like x1 plus x2 plus x3 equals 0. And if I plugged in zeros for all the free variables, say x2 and x3 were free, all I'd get is that the pivots were also 0, and that's not useful. So when we did the null space, we did not set them all equal to 0. We set a lot of them equal to 0 and then other ones equal to 1, so that I would get non-zero solutions. Here we're going to have things like x1 plus x2 plus x3 equals whatever, non-zero numbers. Now I could set x2 and 3 equal to 0 and find what x1 is, and it should not be 0. Okay, so it's okay when I'm finding this particular solution, I can set all the free variables equal to 0. I can set them equal to whatever I want. 0 is something really easy to plug in. So that's why I choose zeros. It doesn't have to be. Some people are getting really stuck like, why are you choosing 0 and 1? Why are you choosing zeros? Because they're easy. You can choose 1/2, 1/3, and 25 if you want. That's going to be a lot harder to plug in, but you can do it if you really want to do that. I'm choosing zeros or zeros and 1 in the null space part because it's easy and you can choose whatever you want. So don't get bogged down in like, what? How come you're choosing zeros? Why are you able to do that? You can set them equal to whatever you want. Free variables, that's where the name comes from. Pick it, pick whatever you want. I'm going to choose zeros here. Solve for what's left. This is called our particular solution. It's one thing that makes AX equals B. We'll denote it with a little subscript P for particular solution. So you'll get one of them. Multiples of this will not work. This is not like what we did in lesson 8, because this is not a vector space. Because AX equals B, when I plug in 0, 0 is not a part of it, right? The 0 vector does not exist in AX equals B if B is not 0. So this is not a vector space, meaning vectors that are in the solution, multiples of those vectors are not. Linear combinations of them are not. I have one right now, and only one. But I can use what we did in lesson 8 to find more. So we'll find the homogeneous solution. All the special solutions that we found in lesson 8, we'll put them together in what we call the homogeneous solution. It's basically the null space. Okay, it's the solutions to AX equals 0. So we'll have a little subscript N, that's for null. Okay, those are the things that make it 0. The complete solution will be our one particular solution, not multiples of it, literally the one, plus all the multiples of the homogeneous solution, all the linear combinations. So think, we're going to have something like one thing that does make AX equal B. And remember our homogeneous solution, all of our little special solutions, we'd have found like 2 free variables, we'd have 2 vectors. 3 free variables, we'd have 3. So here we'd have, like, say we had 2 of them, which is what we have in a lot of our examples and stuff. Oh my gosh. Okay, I might re-mirror here and see if it goes any better. All right, so say my homogeneous solution, this is what we did in lesson 8. I found my 2 vectors and that every linear combination of them should give me 0, which means like AX sub n or A C1 times AV1 plus C2 times AV2 will give me 0. Well, then if I multiply A times the sum of those 2 things, or A times X sub P plus C1 V1, C2 V2, again, whatever vectors you got there, I can distribute. That's something we're allowed to do as long as I keep A to the left. I'm a little faster, but not much. AXP, we already said, is B. AV1 is going to be 0, and AV2 is going to be 0. So this will be another solution, right? That'll also give us B. So if I take all of my homogeneous solutions and I add one particular solution to it, I will have a new solution to AX equals B. Because all those homogeneous ones I'm adding, they're not really adding anything to the B side. They're adding 0. Right? So as long as I just take all those homogeneous solutions, picture this is what we did in lesson 1. My homogeneous solutions here, since I've got 2 of them, they form a plane that goes through the origin. I add the particular solution to shift that plane so it goes through where we need it to go through to get B not 0. It does not go through the origin. This again, this is a plane. It's just not a plane through the origin, so it's not a vector space. Okay, the null space is the homogeneous solution. That'll be a vector space. And then we're just shifting it away from the origin to wherever we need it to be. So that's basically what we're doing here is we're taking all those solutions that give me AX equals 0, and we're just shifting them. We're adding some constant to them so that they go to AX equals B. Okay, not AX equals 0. So that's kind of what we're doing here. So I'll find homogeneous solutions, what we did, exactly what we did in lesson 8. I'll find one particular solution, add them together. That is literally all the solutions to AX equals B that exist. That entire plane worth of solutions or whatever, I've just shifted it to where it needs to be. Okay, so we're going to find complete solution to a system. It's still very slow. There. All right, to this system. Coefficients are ones we've seen in a past set of notes. So that part should be familiar. The right-hand side is different. So we're going to have x1 plus x2 plus x3 plus x4. 1x1, 2x2, 3x3, 4x4 is 1, and so on. So I'm going to make my coefficient matrix here. 1, 2, 3, 4, 2, 4, 8, 10, 3, 6, 11, 14. But I also want to add a column for the 1, 6, and 7. And I'm going to call them B1, B2, B3. For this particular problem, you could put 1, 6, and 7, and you could solve it and get the solution. If we kind of keep track of them as constants, we actually will learn more about the solution than if we plug in 1, 6, and 7. So I'm going to leave them as B1, B2, B3, which just stand for my first B, my second B, my third B, my 1, my 6, and my 7. But again, if you put in 1, 6, and 7 for this problem, just finding the solution, you'll get the solution. You don't really need to put B's there. I'm going to show you what that's going to tell us, though. All right, so to get rid of the 2 in row 2, I'm going to take row 2 minus 2, row 1. And then to get rid of the 3 in the third row, I'm going to take row 3 minus 3, row 1. So we have 1, 2, 3, 4, B1. 2 minus 2 is 0, 4 minus 4 is 0, 8 minus 6 is 2, 10 minus 8 is 2. And then make sure you do it to the last number as well. I'll have B2 minus 2B1. And then I'll have 3 minus 3 is 0, 6 minus 6 is 0, 11 minus 8 is 2, 14 minus 12 is 2. And then I'll have B3 minus 3B1. And we should be able to see, I can still eliminate, right? I can get rid of the first 2 that's occurring in row 3. So I can take row 3 minus row 2, and I can eliminate further. I want to go till the low numbers on the bottom, farthest left, that I can no longer eliminate them without reintroducing non-zeros to the things I've made 0. So I can still do that. So I'm going to do that one more time. So I'll have 1, 2, 3, 4, B1, 0, 0, 2, 2, B2 minus 2, B1, and then 0, 0, 0, 0. I'll have B2 minus 3B1 minus parentheses B2 minus 2B1, right? I'll subtract the entire thing that's in row 2 from row 3. So I'll have B3 minus 3B1 minus B2 plus 2B1, right? Distribute the negative to the entire R2 that I'm subtracting. So I'll end up with B3 minus B2. I'll have a minus 3B1 plus a 2B1, so minus a B1. If you need an extra step to kind of simplify what's happening there, you're just subtracting the third number from the second number in that last column, and then simplifying. Okay, and then we do what we did in lesson 8. We're going to solve for when B is 0. all these equations are equal to 0. So I'm going to have like x1 plus 2x2 plus 3x3 plus 4x4 is 0. And then 2x3 plus 2x4 is 0. The last row we don't really need because that's 0 equals 0, which, yes, that's true, but we don't need it. So I'm taking from my elimination, those equations, I'm going to set them equal to 0 first. Find the homogeneous solution, find the null space, find AX equals 0. Okay, our pivots are in column 1 and 3. So our free variables will be in column 2 and 4. So x2 and x4 are going to be the free variables. Again, I can set them equal to anything that I want. Anything. What I need to make sure I'm doing is, because there's 2 free variables, I should end up with 2 independent vectors. So that's why I choose 1 and 0 and 0 and 1. Because I know there's no multiple of 0 that's going to give me 1. So they're not multiples of each other. Okay, and they're not going to be linear combinations of each other if you have more than 2. If I choose 0, 1, 0, and 0, 0, 1, and 1, 0, 0, I know those 3 are going to be independent. If I choose things like 1, 1, 1, and 1, 2, 3, and 2, 3, 4, those are not independent. There's a linear combination there. So you don't want to, you can choose anything. The reason I choose 1s and 0s is it's easy, and I know I will get independent ones. So I'm going to set x2 equal to 1 and x4 equal to 0. I would start with the second equation because it's got fewer variables. So we'll have 2x3 plus 0 is 0, which means x3 is also 0. All right, when I plug in x4 equals 0 into that second equation, I'll get x3 is also 0, which will eventually appear on the screen because I already wrote it. Then if I use the first equation, I'll have x1 plus 2x2, which is going to be 2, plus 0 equals 0, right? x3 and x4 are both 0, which means x1 would be -2. So I'll have one special solution, -2, 1, 0, 0. Okay, that's one vector in the null space. If I look, I can tell, because if I plug in -2, 1, 0, 0 for x1, x2, x3, x4 into all 3 equations, I should get 0. So like in the first one, I'll have -2 plus 2 plus 0 plus 0 is 0. In the next one, I'd have -4 plus 4 plus 0 plus 0 is 0. In the next one, I'd have -6 plus 6 plus 0 plus 0 is 0. So I can tell this is in the null space, right? This will make my equations 0. Okay, then I would find another one. I want it to be independent of that. I already know every multiple of that will work as well. I don't want one of the multiples. I also already know that 0 will work. 0, 0, 0, 0 will work, but I don't want that either. I have 2 free variables. I want another vector that is different from this one, not parallel, not combinations of this and other ones that I've already found if there's more than 2. 2 free variables, I want 2 of them. So I'm going to let x2 be 0 and x4 be 1. Okay, again, because it's easy and I can set them equal to anything I want, and because I know it will give me an independent vector from the first, because those 1, 0 and 0, 1, there's no multiple that I can multiply by 1, 0 by to get 0, 1. Right? That's what I mean by having it independent. There's no way I can kind of get that same thing. So I'll use those same equations. So I'll have 2x3 plus 2 equals 0. If I use that second equation, x3 is -1 then. And then I'll have x1 plus 2x2, which is 0 this time, plus 3x3, which is a -3, plus 4x4, which is a +4, equals 0. And I'll end up with x1 equals -1. So I have a vector, -1, 0, -1, 1. Obviously not a multiple of the first. Again, if there were 3, I would want to make sure they're not linear combinations of each other, which if you choose 1 and all 0s, they won't be. That's another thing that we're guaranteeing here. Okay, so in my system of equations, again, I should be able to check my work. If I plug -1, 0, -1, and 1 in, I'll get -1 minus 3 plus 4, which is 0, -2 minus 8 plus 10, which is 0, and -3 minus 11 plus 14, which is also 0. So I have another one. Okay, my homogeneous solution then is every multiple of -2, 1, 0, 0, plus every multiple of -1, 0, -1, 1. Okay, I have a two-dimensional subspace of R4. I basically have a plane in R4 worth of vectors that are in the null space. Two-dimensional because there's two vectors. So picture whatever R4 looks like. I've got two vectors in there, and whatever plane goes through those two vectors, that is where all the null space vectors are. Okay, all the multiples of these things. The last thing I do is actually set it equal to what it should be, not just 0. We're going to take those same equations, x1 plus 2x2 plus 3x3 plus 4x4 equals b1. Okay, whatever this is, that's what you want on the other side of that equation. Don't use your original b's. Use what happened to them after you did elimination. So in this case, b1 is just 1, right? It's my first b. And then I'll have 2x3 plus 2x4 equals b2 minus 2b1. It's not equal to 6. Okay, it's equal to whatever happened after you took that 6 and added and subtracted rows. So it was b2 minus 2b1, meaning 6 minus 2 times 1, which is 4. The last equation, I'm going to write it. We normally wouldn't if it's all zeros. Oops. 0x1 plus 0x2 plus 0x3 plus 0x4 equals b3 minus 2 minus b2 minus b1. 7 minus 6 minus 1, 0. So that equation is still 0 equals 0 when it finally finishes writing. Okay, that last equation is still just 0 equals 0, so it's not really that useful. It needs to be 0 equals 0. If you've got zeros on the left, you should have a 0 on the right, and we'll get to that in a second. Okay, but that equation is not going to be super useful for us to solve. So now I'm going to set all my free variables equal to 0. Again, set them equal to whatever you want. It doesn't matter. 0 is really easy to plug in and to evaluate. So I'm going to use zeros. You can use something else if you really want to. Don't get bogged down into why does it have to be 0. It doesn't have to be 0. You can use anything you want. So then we'll have 2x3 plus 0 equals 4. Okay, this is why we can choose zeros, because that won't make x3 0. It's going to make x3 2. And then we'll have x1 plus 2x2, okay, which is 0, plus 3x3, which is 6, plus 4x4, which is also 0, equals 1, which means we'll get x1 equals -5. So this is our particular solution, xp. -5, 0, 2, 0. And again, we could check our work. Go back to your system of equations. This should literally be a solution to them. When I plug in -5, 0, 2, 0 to each of the equations, I should get 1, then 6, then 7. So here I'd have -5 plus 6 is 1. I'd have -10 plus 16 is 6. And then I have -15 plus 22, which would give me 7. Okay, this is one solution. We have infinitely many. Our complete solution will be the homogeneous solution plus the particular solution. This would be your final answer. And I'm fine if you've labeled them with you not having to rewrite them all out. You could write C1 times that vector plus C2 times that vector plus that third vector. Or if you label them, just say you'd add them together. Okay, but that would be your final answer. But for example, we could get more solutions. Okay, I could add the 3 vectors together. -8, 1, 1, 1. That's another solution. Okay, I just added the 3 vectors together. I'll have -8 plus 2 plus 3 plus 4. So -8 plus 9 is 1. I'd have -16 plus 4 plus 8 plus 10. Okay, which would give me my 6. And then I'd have -24 plus 6 plus 11 plus 14, which is 7. Okay, I could get another one. I could just be literally come up with infinitely many solutions by taking XP. This one, I'll add 2. I'll make C1 2 and C2 0. So I'll take 2 of the first vector, 0 of the second, and then add XP. So I'd have -9, 2, 2, 0. That's another solution. Okay, and you could keep doing it. You don't have to, okay, unless the problem's asking for examples or asking for more solutions. You don't need that part, but that's what we mean by this, is that I could take my particular solution, any linear combination of the homogeneous solutions, and I could get another set of solutions. So there's infinitely many here. Okay, R is not equal to M or N. So in this case, there's many solutions for this B. Okay, so notice after we did elimination to get U, we ended up with a row of zeros. That won't always happen, but if it does, that's giving us a constraint on our equation on what B can be. So here again, we got 0x1 plus 0x2 plus 0x3 plus 0x4 equals B3 minus B2 minus B1. Well, there is no x1, x2, x3, or x4 that I could plug in here and not get that B3 minus B2 minus B1 must be 0. Okay, only because it's a row of zeros. People start trying to equate this to other things. Whatever I get on the left, the right has to add up to that same thing. No, it's literally because I got a row of zeros. That third equation is 0 times each variable equals the thing on the right side. Well, if I take 0 times every variable, add them together, the right side must also be 0 in that equation. So only for a row of zeros. If you have no rows of zeros, there are no constraints. That is where you have R equals M, meaning there is a solution for every single B. Okay, that's what we already talked about. If you have no rows of zeros in U, all the rows are independent. There's a pivot in every row. R equals M, whatever. All that stuff that we said was the same. It means every B will have a solution. If you get a row of zeros, R does not equal M, meaning some Bs will have solutions, some will not. This is how you tell. When I get a row of zeros, what I get on the other side must also be 0. So for example, if I had B equals 1, 1, 1, I would have stopped and said no solution. Eventually that'll show up. Okay, if I had B equals 1, 1, 1, there's no solution because 1 minus 1 minus 1 is not 0. So annoying. I figured if I kept talking, it would eventually show up. All right. Try this again. Oh, now it's not even going to connect it. There we go. All right. If I had had 1, 1, 1 as my right sides of the equation, I would have known there was no solution. And I would have known it before doing a lot of the work. I would have known it here. Okay, at this step, I would have stopped. And if I had had 1 and 1 and 1 on the right sides of those equations, I'd say, no, there is no solution. Okay, 7 minus 6 minus 1 is 0. So we know there's going to be a solution there. So if I had 1, 9, 10, there is a solution. If I had 1/2, 1.5, and 2. Okay, there's a solution. as long as B3 minus B2 minus B1 in our thing gave us 0, we know there's a solution. That's on the plane we need it to be on. If it doesn't equal 0, then it won't be. Okay, it's a different vector on a different, not on the plane that we need it to be on. It's not in that place that we need it to be. B3 minus B2 minus B1 is 0 is not a formula. Okay, it doesn't have to be true all the time for every system. It's this system of equations. Because we got a row of zeros on the left, the right had to also be 0. If you get multiple rows of zeros, you'll have multiple conditions that need to be true. So if I ended up with 2 rows of zeros when I did elimination, for each row of zeros, I will have some combination of B's that would also have to be 0 in order to have a solution. Okay, so this is kind of how we know what types of B's work, what types of B's do not work. In this case, B3 minus B2 minus B1 would have to be 0 in order for there to be a solution. And so you could pick any B's you want, and I could tell you, yes, there's a solution, no, there's not. If it's no, there's not, don't do the rest of the work. Okay, you stop there and you say, no solution. Okay, this is what we call a consistent system of equations. Consistent means that for that given B, there is a solution. So like the system we just solved, it's consistent because there was a solution. In fact, we just showed there was infinitely many solutions. As long as there's at least one, we call the system consistent. If we did the same one, one, 3, 5, we would say it's inconsistent or not consistent. Either one's fine. Okay, AX equals 1, 3, 5, not consistent. Because in this system of equations, 5 minus 3 minus 1 would have to be 0, and it's not. But if we had had AX equals 1, 0, 1, that would have been consistent. It would have different solutions than what we found, but there would be solutions because 1 minus 0 minus 1 is 0. Okay, so if we kind of keep track of what's happening to the B's, any row of zeros will tell us. If there are no rows of zeros, it's consistent for every B. Okay, if there are no rows of zeros, M equals R, which means there is always a solution no matter what B is. So if I do elimination and as long as you've done it completely, you've finished elimination, no rows of zeros tells me it is always a consistent system. Okay, rows of zeros will tell me it's only consistent for certain B's. All right, so we'll do our last example and then we'll be done here. So this one says, eventually we'll say, for what B's will the system be consistent? Find a solution for one such B. Meaning find what can work and then just pick one that works and solve it. So this one's a pretty easy one. So I'll put my coefficients and then I'll also put a B1 and a B2. And I do elimination by trying to eliminate the 2 at the beginning of row 2, the number at the beginning of row 2. So I'm going to take row 2 minus 2, row 1. And I have 1, 3, 5, B1, 0, 0, 0, B2 minus 2, B1. Again, if you don't get any rows of zeros, it's consistent for every B. You don't have to, there are no constraints. Every single row of zeros you see gives you another constraint that has to be true. This is consistent when B2 minus 2B1 is 0. I cannot emphasize enough, it's only because it's a row of zeros. If it is not a row of zeros, if that was 0, 0, 1, B2 minus 2B1 does not have to equal 1. The 1 is a coefficient of a variable. The variable would have to equal B2 minus B1, but that could be anything. Okay, the coefficients are zeros, which means that you will have 0 on the left and therefore would have to have 0 on the right. So it's only a row of zeros, not whatever's in the last row, which is what people equate this to and start doing on the homework and the test. It's not whatever's in the last row. It's because the last row is zeros. So consistent when that's true. So for example, we could choose B equals 2, 4. All right, 4 minus 2 times 2 is 0. You could basically choose any multiple of that. Here, our B's lie on a line together. The possible B's, the column space here would be on a line. So our possible B's that could come out of this have to be on the same line with this thing. So we could solve for B equals 2, 4. So we'd have x1 plus 3x2 plus 5x3 equals 0. Our second one would be 0 equals 0. Again, second equation is not super useful here. We have a pivot in column 1, none in row 2. So meaning x2 and x3 are our free variables. So we're going to end up with 2 vectors in the homogeneous solution. We need 2 different vectors in the null space to make ax equals 0, however you want to think about that. So we're going to let x2 be 1, x3 be 0 to get one of them. So I'll have x1 plus 3 equals 0, which means x1 is -3. We have -3, 1, 0. Again, plug it in for x1, x2, x3, and you should see that you'll get 0 for both equations. Okay, or take the dot product of this and the rows of A, and you'll get 0 for both. Now try x2 equals 0, x3 equals 1. Plug it in, I get x1 plus 5x3 equals 0. That's a 3. Which means I'll have -5, 0, 1 as another choice. Okay, obviously those are independent. They are not multiples of each other, they're not linear combinations of each other, however you want to think about that. So my homogeneous solution is any multiple of -3, 1, 0 plus any multiple of -5, 0, 1. Again, I have a plane, a subspace of R3. Okay, I'm in R3, I have 2 vectors, and the whole plane that goes through those 2 vectors would be other things in the null space. Okay, other things that would make ax equals 0. Then I'm going to go and actually use the B's that I've got. So I have x1 plus 3x2 plus 5x3 equals B1. So again, make sure you look at what happened to your specific B's. So here I'm using B1 here. B1 is just 2. Then 0x1 plus 0x2 plus 0x3 should be B2 minus 2B1, which is 0, which is true, but again, not a useful equation, so don't really need to write it. But it does need to be true still. That second row, that needs to be true still. Now I'm going to let my free variables both be 0. And I get x1 equals 2. That's my particular solution. 2, 0, 0. And again, if I now take the dot product of row 1 in that column, I'll get 2. The second row in that column, I'll get 4, which should happen. That is not my only choice. You could find other ones if you'd rather. Then my complete solution is that homogeneous solution, all those vectors plus our one single particular solution, not a multiple. You cannot take multiples of the 2, 0, 0. You could find a different one, but it's not multiples of that one. You could find a different XP if you'd rather not use zeros for whatever reason. So again, I could make C2 be 5, make C3 be -3, add XP. That's another solution to my system of equations. So I've taken basically the null space solution that's on a plane, and I've just shifted it up away from the origin. to get my particular solution, which that whole solution, the complete solution, is not a subspace. Okay, I cannot then take multiples of my complete solution. I can take multiples of the null space part, but not the XP part. So this would be my complete solution here. Okay, so again, this one you could have also done infinitely many things because you could have chosen other B's. The way this is worded, you could have picked it for a different B. All right, that's all. We only have a couple minutes left. If you guys have questions, we also have tomorrow and Friday. You can ask questions. Monday probably won't have time because it's a group thing and that usually takes most of the period. But tomorrow and Friday, we have all day that you guys can ask questions if you have anything that you're stuck on or not making sense. If you guys have something you need right now, you can stick around and let me know. Otherwise, you guys have a good rest of your day and I'll see you guys tomorrow,
Wait, when's the group thing?
Monday.
Thank you.
Uh-huh.
Mr. Smith?
Yeah.
For that pie poster thing,